Imagine this. A tiny red star 39 light-years away has 7 planets the size of Earth. Among them, Trappist, 1E orbits in the Goldilocks Zone, not too hot, not too cold, where liquid water could exist if a planet has air. Early Webb telescope data gave tantalizing clues of an atmosphere on Trappist, 1E, including hints of methane, but the signals were weak. The first 4 Webb transits of 1E couldn't confirm any atmosphere yet. Scientists are left narrowing down possibilities. Maybe a global ocean world, or a Titan-like methane planet. In short, Trappist, 1E could be our best shot at finding life beyond Earth, but we need more data to know.
Trappist 1 is an ultra-cool red dwarf star, about 8.9% the mass of the Sun, and only 12% its radius. All 7 planets, named B through H, orbit closer to the star than Mercury orbits our Sun. For example, Trappist 1E circles at about 0.0293 astronomical unit, with a year of only 6.1 Earth days. By comparison, Mercury orbits at 0.38 astronomical unit, with an 88-day year. So 1E is about 13 times closer to its star than Mercury is to ours. Even though that's very near, its star is so dim that 1E receives only about 60% of Earth's sunlight. In Trappist 1E sky, the red star would loom 4 times bigger than our Sun does here, bathing one side of the world in perpetual sunset red light. The system was discovered by catching tiny drops in starlight as each planet passed in front of the star. Because the star is small, each planet blocks a larger fraction of light, making the signals easier to detect.
Out of the 7 Earth-sized planets, E stands out. It sits in the star's habitable zone, meaning its temperature could allow liquid water if it has air. Trappist 1E is also nearly Earth's twin in size and mass, about 0.92 times Earth's radius and 0.69 times its mass, giving it Earth-like surface gravity and density. We even know it's rocky, probably iron and rock like Earth. Because it's so close to the star, it's likely tidally locked. One hemisphere always faces the star, the other always dark. This half-day, half-night world would have a blazing day side and a freezing night side. To be habitable, you would need an atmosphere to circulate heat and maintain pressure, along with liquid water. Models show that a moderate atmosphere of nitrogen and some greenhouse gases could redistribute heat, so water might pool as a global ocean or at least around the sunlit side.
So what atmosphere could 1E have? Webb's early results already ruled some out. Any original hydrogen or helium envelope is almost certainly gone, blown away by the star's early activity. A thick Venus-like CO2 atmosphere or a thin Mars-like atmosphere also appears unlikely. Instead, possibilities include an Earth-like mix, mostly nitrogen with some CO2, water vapor, or even methane to boost the greenhouse effect. With about 1 bar of pressure, heat could be transported to the night side, so oceans wouldn't freeze completely. Alternatively, a methane-rich atmosphere like Titan's could behave differently, absorbing infrared and cooling parts of the atmosphere before heat reaches the surface. In that case, water might only exist under the permanent day side or near the twilight region. Such conditions could still allow life. Importantly, the methane hints seen by Webb might not even be from 1E. Trappist 1 itself can contain methane in its outer layers. Scientists now think the methane signature to be stellar noise, without strong CO2 or water signals. We simply don't know if 1E has any thick air at all. Here's how Webb tries to decide. During each transit, starlight filters through any planetary atmosphere and leaves absorption fingerprints. Webb's instruments record tiny dips at specific infrared wavelengths. Carbon-hydrogen bonds and methane and carbon-oxygen bonds in CO2 absorb known infrared colors. After 4 transits, the spectrum from 1E is nearly flat. That could mean either no atmosphere or a cloudy one. One model suggests a clear, thin nitrogen-rich sky with trace methane and little CO2. JWST data already rules out a puffy hydrogen envelope and disfavors a dense CO2 blanket. Encouragingly, it still leaves room for a modest atmosphere that could allow surface water. The signal is extremely delicate, so scientists must be sure they're not seeing the star's own fingerprints.
TRAPPIST-1 is not a gentle Sunday. It's a small red dwarf around 2,500 K that shines mostly in infrared and lives for trillions of years, but had a stormy youth. Observations show frequent powerful flares comparable to the largest solar flares. With the planets so close, those flares and intense radiation hit them relentlessly. Models suggest such flares could strip a planet's atmosphere away. Over time, 1ES atmosphere might struggle to survive. A magnetic field could help if the planet has a molten core, but it would need to be extremely strong, far stronger than Earth's. The star has calmed somewhat with age, but any atmosphere that exists is still balancing between erosion and replenishment.
Despite the odds, life-friendly niches might exist. If 1 has even a thin atmosphere, simulations show the twilight band between day and night can maintain liquid water. Even a cold world isn't hopeless. An ocean under ice warmed by hydrothermal vents, like Europa or Enceladus, is possible. Methane would break down relatively quickly under the star's radiation, so any methane hint would require ongoing sources. The key question remains simple. Does TRAPPIST have an atmosphere? To answer that, scientists are scheduling many more transits with JWST. Some observations will occur simultaneously with TRAPPIST-1b, which is likely a bare rock. By comparing the two during a double transit, researchers can subtract the star's behavior and isolate one yes signal. This planetary calibration could finally reveal faint gases like CO2 or rule out an atmosphere entirely. In the coming years, JWST may tell us whether TRAPPIST-1e is a watery paradise, a methane world, or a dead, airless rock. Either outcome will teach us something fundamental. Right now, 1e remains one of the most promising habitable zone planets known. The latest data already ruled out Venus-like and Mars-like scenarios and left the door open for Earth-like possibilities. With more transits and improved analysis, scientists expect to determine whether a nitrogen-based atmosphere exists and whether carbon dioxide is present. Finding life isn't guaranteed, but discovering a true Earth analog in our galactic backyard would be historic. The hunt for an alien world just got very real.